Hi everyone. So this video lesson is about the concept of work. So we're looking at work here, and that doesn't just mean physics work, but it's actually a term in physics that means something else. So we're just going to start with the definition of work. So work is a physical quantity that is a result of the application of a force and the displacement of an object. Okay, so work is actually force with the displacement that goes with it in terms of an object. What that means is that if we didn't apply a force, then there's no work done on the object. If we didn't have a displacement for the object, then there's also no work. So if we have no force, that's going to mean no work. Or if we have no displacement, that's also going to mean that we have no work. Okay, and so it is just a physical quantity. It's a calculation that we're going to be doing, and it's basically a calculation of how much force versus how much displacement our object is experiencing because of that force. Okay, the symbol for work is a capital W, and it is a scalar quantity, which means there is no direction associated with it. So no direction, right? It is not a vector quantity, but a scalar quantity. So no direction associated with it. Okay. Our formula for work. So work is actually equal to our force and then something called a dot product, which we're going to talk about, times our displacement. Okay, now I just want you to remember that force and displacement are both vectors. So this little dot that I've drawn in the middle is something called a dot product. It's just a fancy way of saying that we're multiplying vectors, and we're going to multiply these two vectors to actually get a scalar quantity, which is work. Right? So work is our scalar quantity. So we are going to take our force vector times our displacement vector, and we're going to actually end up with a scalar quantity, and that's going to be work. Okay? And so what the formula starts to look like is we have our work is equal to our force times our displacement, and so we know both of those are vectors. And then cos of the angle in between them. Okay, so this angle is the angle between the force and the displacement. Sorry, this should have been a delta D up here. Okay, so in order to calculate the work, we need to take the force that we have, we need to multiply it by our displacement, and then we're going to multiply it by cos of the angle that's between the force and the displacement. What this means is that we need to have a really good picture of where our force is going in terms of direction and where our displacement is going in terms of direction. The other thing is that those vectors should be joined at the tail. So our vectors are not going to go from head to tail. They're going to be attached tail to tail. And so we are actually going to talk about all the different situations that we could have with that. We're going to look at every single sort of different picture that we could possibly get. I just want to talk really briefly here about the unit for work. So we know that force, So we know that force has a unit of newtons. So it's going to stay newtons, okay? And we know displacement has a unit of meters. work is going to end up with this unit of joules. And so this is a joule. Okay, and so the unit for joules is a J. If you want to say it in words, we'd say joules, and it's Joule. Okay, and so that's the unit for our work. So when we take our force in newtons times our displacement in meters times cos of the angle in between the force and the displacement, we're going to end up calculating work, which is measured in joules. All right, so the different ways that our force and our displacement could be connected. So we could have, so I'm going to draw our force in red and our displacement in blue. So we could have this situation where force and the displacement are happening in exactly the same direction. So this is same direction. When we do that, the angle between them is 0 degrees. Okay, that doesn't actually make the work 0 because cos of 0 is actually 1. And so we end up taking the full force times the full displacement times cos of 0. Okay, so we could have them in the same direction. We could have our force, so that's one situation. We could have our force going up in some direction and our displacement still staying horizontal. So say we have this arrangement here. In this arrangement, that angle is somewhere between 0 to 90 degrees. Okay, they're going in roughly the same direction, but I mean, obviously this specific picture is definitely not 90 degrees, but it's a little less than 90 degrees, but a little more than 0 degrees. Okay, and so our angle in there is going to be not 0, but also not any higher than 90 degrees. And so likely we'll be given that angle in the actual question. So the force and the displacement aren't going in exactly the same direction, but they're going in roughly the same direction or somewhat the same direction. Okay, we could also have a situation where our force is, say, going up like this, and our displacement is still horizontal. And in this situation, we have a theta of, not of 0, silly. We have a theta of 90 degrees. Okay, when theta equals 90 degrees, okay, if we know that cos of 90 is actually 0. That's just a little trig for us. That means that the work in this case is always going to be 0 joules, because we are going to have to take our force times our displacement, but we're going to have to multiply it by cos of 90 degrees, which is 0. Which means no matter what our force or our displacement are, if they're 90 degrees to each other, we have 0 work. That is always going to come out to be 0 joules. Okay, so when they're 90 degrees, you can tell right away. You don't even have to do the calculation. You can know right away that the work is going to be 0 if the force and the displacement are 90 degrees to each other. All right, we can have another situation where our force is, say, off in some direction over here, and our displacement is still horizontal, going to the right here. So that's what our force and our displacement look like. There, the angle is definitely greater than 90 degrees, okay, but it's an obtuse angle. So it's, 110 degrees or 125 degrees, or it's definitely not 180, but it's greater than 90 degrees. When this happens, the work actually becomes negative in value. And so that's a possibility. You can actually have negative work. That is absolutely a possibility. Okay. Our last situation in terms of directions is, say our force is going completely opposite the direction of our displacement. So here, our angle is 180 degrees. Okay. When that happens, our work is still going to be negative, okay? Because cos of 180 is -1, okay? And so we're still going to have that negative work, okay? It's tricky because you really have to draw yourself a picture so you know which direction our force is going, which direction our displacement is going, so that we can use the correct angle in our work formula. So we're going to do a couple of practice questions. So practice number 1. So in practice question number 1, we have someone is cutting a lawn with a lawnmower. So I need to draw a lawn here. So we've got some grass, and then maybe we'll make our lawnmower red. And then put some wheels on our lawnmower. And we've got our handle for our lawnmower up here somewhere. And our person pushing our lawnmower. Okay. And so the question is going to tell us that we are pushing the lawnmower with an applied force that is 125 newtons. And the question is also going to tell us that it's at an angle of 40 degrees below horizontal. And we're pushing it for 12 meters. So we want to calculate the work in this question. So the first thing I want to do is draw a free body diagram for my lawnmower. So if we think about my lawnmower, I have a normal force that's pushing up on the lawnmower, but I also have a force of gravity that's pushing down, and I have that applied force, but my applied force is not horizontal. My applied force is going at an angle of 40 degrees below horizontal, which means my applied force is somewhere like this. And it's down 40 degrees. Now my motion is going forwards, which means that's the direction my displacement is going. So if we line up our displacement and our motion vectors, so this is our displacement, and my motion, or sorry, my force is down here. There's a 40-degree angle between them. So that means that I know my angle is 40 degrees. So to calculate my work, I'm going to do my applied force times my displacement times cos of 40 degrees in this case. So my applied force was 125 newtons. My displacement is 12 meters. And then I'm timesing that by cos of 40. So then I'm just going to do the math. And I should get, let's see, 1,149 newtons, which I then need to round for my sig figs, because I would want 2 sig figs. Oh, newtons, not newtons. Silly. Sorry, not newtons. It should be in joules. Getting ahead of myself here. So then we should be in joules. Or if we wanted to convert this to kilojoules, that also would be fine to say as 1.1 kilojoules. Converting from joules to kilojoules is the same as converting from meters to kilometers. Okay, so joules to kilojoules, we're going to divide by 1,000. If we want to go kilojoules to joules, we would multiply by 1,000. Okay, and so that's going to be our final answer for that practice number 1. So let's try a second practice question. So we'll try practice number 2. So in this one, we have a father pulling a child on a toboggan that's along a flat surface with a rope angled at 35 degrees above the horizontal. Okay, so we've got probably an ice or snow surface, and then we've got our toboggan. So we've got our father pulling the rope, and we've got the child sitting in the toboggan, and it's saying that the rope is angled 35 degrees above horizontal. So if we draw that in here, that's the angle of my rope. My question is going to tell me that the work done by the father is 2,410 joules, and the displacement is over 50.0 meters. Okay, and so this work is from the applied force. And so this is the work that's done by the father by pulling the toboggan. So we're going to determine the work done on the toboggan by the normal force and by the force of gravity. Okay, so here we're looking for the work for our normal force, and we're looking for the work for our force of gravity. Okay, so we don't have either of those, and we're looking to find both of those. So the first thing I want to do is draw a free body diagram for my toboggan. So I have a normal force that's pointing up. I have an FG that's pointing down. I had my F applied that was up here at 35 degrees above horizontal. And I know that my motion is in this direction, which means my displacement is horizontal. Okay. Now, one thing I want to show you is that it seems like we don't have enough information to find the work for the force of gravity or for the normal force because we don't know the mass of the toboggan with the child. But here's what I want to show you. If we were to line up the force of gravity with our motion, that angle would be 90 degrees. And when we have an angle of 90 degrees, we know the work is 0. Okay, if we did the same thing with our Fn, same thing's going to happen. We have an angle of 90 degrees, which means the work for our Fn is also 0 joules. And so even if you think you don't have quite enough information to calculate the work, have a look and see if the angle will help you calculate it for you. Okay, so if you have an angle of 90 degrees, you can know right away that that work for that force, right, as long as the force and the displacement are 90 degrees to each other, the work for that force is going to be 0 joules. And so you can easily and quickly answer that question, even if you don't think you have enough information. All right, so those are the 2 practice questions. There are some more practice questions for you to work on your own. Make sure you have a look at the answer key to help you out with the extra practice questions. And that's all there is in terms of the